Have you ever stopped to think about how your video call stays so perfectly in sync, or how your phone's GPS just nails your location every single time? Well, it all comes down to this invisible pulse, this kind of secret global heartbeat of perfect timing that powers our entire digital world. Let's pull back the curtain and see how it all works.
Right, this perfectly synchronized world we live in, it doesn't just happen by magic. It's all built on a system with almost unimaginable precision. Every single packet of data, every time your phone seamlessly switches between cell towers, every financial transaction, it's all choreographed by time. So the big question is, how is that time even kept? And maybe, more importantly, how does it get from some master clock somewhere out there all the way to the device in your hand without getting totally scrambled?
Okay, to really get a handle on this, we have to start with this big number: 9,192,631,770. Now, what on earth is that? It's not a lottery number. It is the official number of ticks, or you can think of them as tiny vibrations from a cesium atom that make up one single official second. That's our yardstick.
All right, so that brings us to our first stop on this journey. Our story has to begin with the master clock. We're zooming way out to find the ultimate source of that perfectly measured second for the entire planet.
This definition right here is the absolute key. What it does is it takes this abstract idea, time, and grounds it in a physical reality that is constant and unchangeable. By tying our second to the natural, incredibly stable frequency of a cesium atom, we get a standard that works the same everywhere. This atomic precision, it's the bedrock for everything else we're going to talk about.
So who are the keepers of this atomic time, the Time Lords, so to speak? Well, globally, it's a system called Coordinated Universal Time, or UTC. And here in the United States, the master sources, the real top-tier clocks, are kept by the U.S. Naval Observatory and the National Institute of Standards and Technology, or NIST. These places provide the ultimate time reference for basically the entire country's critical infrastructure.
But here's the twist. Having a perfect clock sitting in a lab is great, but it's only half the battle. Getting that perfect time signal out to billions of devices all over the world, that's a whole other can of worms. That journey is actually incredibly perilous and full of things that want to mess up that pristine signal.
This journey works like a waterfall, a hierarchy. It all starts at the very top, the source, with those master atomic clocks. From there, the signal gets distributed through things like GPS satellites and fiber optic cables to what are called primary reference clocks. Then, it travels through all the local network gear, routers, switches, each with its own clock, all the way down until, bam, it finally hits the endpoint, which is your computer or your phone.
And here is a really important point. This quote from our source material says it all. Each one of those steps, each node in the chain, isn't just a dumb repeater passing the signal along. It's an intelligent repeater. It has to actively clean up the signal before passing it on. So, why? Why does it need cleaning?
Well, because of this guy right here, signal degradation. It's the villain of our story. As that timing signal travels, it's like a game of telephone. It just inevitably gets a little bit corrupted by noise and interference. And these tiny little timing errors, if you don't fix them, they start to add up and would eventually cause total chaos on the network.
This brings us to the real unsung hero of this whole story. It's a device that lives inside every piece of network equipment, and its whole job is to fight that degradation. So, to see how it works, we have to zoom in to just one of those network nodes and meet this little champion.
And here it is. It's called a phase-locked loop, or PLL for short. Now that sounds super technical, I know, but its job is actually pretty simple to understand. It takes in a messy, noisy timing signal from upstream, and it generates a brand new, squeaky clean signal whose timing, its phase, is perfectly locked to that original reference.
So how does this magic box work? Well, it's basically doing a four-step dance over and over and over incredibly fast. First, it compares the messy incoming signal to its own little clock to see what the error is. Second, a filter smooths out all the jitter in that error measurement. Third, a special oscillator uses that smooth signal to generate a fresh, clean new clock beat. And finally, and this is the secret sauce, a feedback loop makes sure this whole process repeats constantly, keeping that new clock perfectly in line. Okay, so you might be thinking, great, just stick a PLL and everything and we're done, right? Ha! If only it were that simple. This is where the real engineering artistry comes in, because it's all about a really critical balancing act. So here's the challenge. The little component inside the PLL that actually creates the clock beat, the oscillator, can be a bit, well, flaky. If it's sensitive to things like temperature, its timing will drift a lot in between those corrections from the feedback loop. And what you get is this big, jagged, sawtooth error. The timing is constantly overshooting and undershooting where it should be. The goal, of course, is this. You'd use a really stable, high-quality oscillator that barely drifts at all. And you can see here, the result is a much, much smaller error. The timing is way more precise. The only problem? Those super stable oscillators can be really expensive and use a lot of power. So, is there a better way?
Oh, you bet there is. And this is just so clever. Check it out. An engineer can take that same less stable, cheaper oscillator and still get a tiny error. How? By simply making the corrections way faster. By tightening up that feedback loop, you never give the oscillator a chance to drift very far. It is a perfect example of taming a flawed component with just really smart system design.
And this brings us to the core engineering choice, what they call the loop bandwidth, which is basically just how fast those corrections happen. If you choose a narrow bandwidth, you're great at filtering out noise from the reference signal, but you're slow to lock on. If you choose a wide bandwidth, you lock on super fast and track changes really well, but you let more of that reference noise pass through. So engineers have to pick the perfect balance for every single application. So why do we go through all this trouble? We've gone from atomic clocks in labs to global distribution networks all the way down to these complex little feedback loops. Why? It's all to fight the two biggest enemies of data, jitter and wander. These are the two main ways timing can go wrong. Jitter is a high-frequency thing. Think of it like trying to write with a really shaky hand. It causes immediate errors because the system literally can't tell a 1 from a 0. Wander is different. It's a slow, lazy, long-term drift. Think of your handwriting just slowly drifting off the page. It won't cause an error right this second, but over time it leads to huge problems like buffer overflows, which is why a video stream might just freeze and die.
And the payoff for winning this fight against jitter and wander? Well, it's pretty much our entire modern world. This invisible, perfectly timed pulse is what stops your video call from glitching out. It's what ensures financial data is secure. It's what enables your phone to switch from one cell tower to the next without dropping your call. It's what makes high-speed internet high speed. It's the hidden foundation for almost every piece of tech we rely on.
But here's the thing. This incredible hidden system of timekeeping is already being pushed to its absolute limits. New technologies like 5G, autonomous cars, and the Internet of Things, they're demanding even crazier levels of synchronization, down to the nanosecond. So that leaves us with one final, huge question. What's the next master clock going to be? What will power the next generation of technology?